Welcome back. The goal of this video is to give you an introduction to the common factor model. And let me just stress, this is only an introduction. Factor analysis is a vast topic with large books written about it, and I'm just going to give you the first introduction to it. I want to start by pointing out that factor analysis is not the same thing as principal components analysis. So principal components analysis starts out with some X variables, and you can think about it in different ways. You could think of it as I'm going to find a lower dimensional subspace that optimally, in some sense, describes the original X's, or you can think of it as a rotation of axes, and those are equivalent ways to think about principal components analysis. Factor analysis, on the other hand, is really a statistical model, and I'd like to go over that model with you. So the common factor model I show over here as my X's are being created by their relationship with some lower dimensional latent variables. And these latent variables are called common factors, otherwise known as F's. And so in my notation, what I have here is, let's say I've got two latent variables. So often we draw a picture that looks something like this. So I have F1 and I have F2. And these two latent variables are things that I really think exist, but I can't measure them directly. Okay, so for example, we talked about math ability and verbal ability in the previous video as one of the classic examples of latent variables. So I can't just take a ruler out and measure a person's math ability. The only way I can study a person's math ability is through studying manifestations of that ability, like that person being able to solve certain problems, while someone with lower ability could not solve those problems. Alternatively, it could be just a physical quantity that I'm trying to measure, but my measuring device is not exact. So there are errors associated with my measurements. Think about your science classes, lab science classes that you've taken in the past, and you measure something once, you measure it again, and they're a little bit different because the precision of your measuring device is not perfect. Okay. So we're going to assume that there are k of these latent variables that I cannot measure directly, and I observe a bunch of manifestations of these latent variables, and so these are my X's. So this is X1, X2, X3, X4, and say X5. So I observe these 5 things. Now the common factor model says these things that I'm measuring are really a function of 2 things. There are these unobserved factors. So each one of these has a causal relationship with these X's. So your math ability, whatever that is, will cause whether you get this problem right or not. Likewise, your verbal ability may have some influence on that. But the factor analysis model also allows for other stuff to have an effect on this. And so this other stuff we're going to call errors. So we could call this E1, E2, E3, E4, and E5. So maybe you get a certain problem right on the test just because you guessed right. If it were a multiple choice test, that would be an example of an error. It's not reflective of your ability with math or verbal ability. You just happen to guess it right. Okay, so the way we write this mathematically is that my X's, so this X is I've got P equal to 5 X's here. So this is going to be a P by 1 vector, is going to be some function of my F's. So the function is going to be a linear function. And so we're going to take loading vectors times my common factors, and then I have my errors. So what are these loading vectors? Well, in this case, my loading vectors will be a p by k, or 5 by 2 in this particular case. This is going to be a 2 by 1 quantity. This is going to be a 5 by 1 quantity, exactly like I have in this picture. And so the way to think about this is this would be the value. L is going to be a matrix. So let's just go write that matrix out. L is going to look something like this. So L11, L21, all the way through L51. We're going to have L12 all the way through L52 in my specific picture. So L11 is going to be what is the relationship between whatever my first factor is and my first observed variable. This would be L21. So how does the second variable get impacted by the first factor? While this line right here is going to represent L12, how does the first variable get affected by the second factor? All right, so that's the basic picture of my model. Now I have a whole lot of assumptions that I'm going to be making about the terms in this model. So these loading vectors are fixed constants. You could call them parameters that are going to be estimated by the model. But these factors are random variables. So we're going to assume that the expected value of these factors is 0. I'm going to assume that the factors have a variance matrix that is the identity. Okay, so what that means is up here, the variance of f is going to look something like this, 1, 1, 0, 0. So the fact that my factors have mean 0 and variance 1 implies a couple things. So this implies the f's are, you could call them standardized variables. So they're standardized and they have mean 0 and variance 1. And my model right now is assuming that they're uncorrelated with each other. Now we're also going to be assuming that f is normal. And so when you have uncorrelated normal random variables, that also means they're independent of one another. But suffice it to say, our f's are uncorrelated. Now, what do we know about these errors? Well, we know certain things about these errors. The variance of these errors will be some diagonal matrix psi that looks like this. So that's a capital psi, and you can draw it like this. So psi 1 all the way through psi 5. We can write the fact that it's diagonal in a shorthand way like this. So all the off-diagonal elements are 0, meaning the error that affects whether or not you got this one right is unrelated to the errors that determine your performance on the second measure that I have. All right. Well, let's now state a couple results. So there are really two main results that I want to go over with you concerning this. And so the first is the variance of x. So I'm actually going to derive this for us. So what is the variance of my x vector that I've observed? Let's make this a little bit smaller so I don't run out of space. We're going to denote the variance of x by a p by p matrix, capital sigma. So this is not the sum sign. This is the population variance matrix. So if we could know the variances by, say, doing a census, then that would be my sigma. And it tells me the relationships between the x's as well as the variability of individual x's. So what is this? Well, we can just go drop in our definition of what x is. So x is equal to L times F plus E. Now, I'm just going to go off to the side here for a second and remind you of a couple, a very important result from univariate probability theory. So back in univariate probability theory, if you had two random variables, say x and y, and a and b are constants, we can find the variance of this sum as follows. This is just going to be a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance of x and y. All right, well, we're going to apply that to this expression. Now remember, these L's are constants, and this has to get squared, but this is a matrix. And so there's an equivalent version of this formula for matrices. And basically what it says is this. Let me just write, if you have some matrix A times X, this is just going to be A times the variance of X times A transpose. So that's a kind of the equivalent version of just part of this formula. Anyway, that's a lot of talking to get to this. So this is going to be L times the variance of F plus the variance of E. And then I've got to worry about the covariance between these, but if you go back to my statement of the problem here, what I've assumed is that the E's are independent of my F's. Okay, so what that means is the covariance is 0. So I'm just going to write a plus 0 here. Oh, and I forgot this. There's an L transpose in there. So when you take A take A out, it has to be like squared. So let's go simplify this. That is I. And the what are the variances of these errors? Well, that's my capital psi matrix. So what we're left with is L times L transpose plus psi. And so this is a really important expression that says that the variance in my in an X can be found by just computing this L transpose or L transpose thing. So just let's go write out some of this. I don't want to write the whole thing out because it's kind of big, but let's remind ourselves what L is. So L looks something like this. So L11 through L51. Then we have L12 through L52. So that's my L matrix. And let's go take the transpose of this. So this is going to be L11, L12, dot, 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 L51, L52. And so when I do this product, what I'm left with is this, L11 squared. So that's this times this plus L12 squared. Now I could do the same thing if I wanted here. I don't want to write everything out. Let's just do a dot, dot, dot. This would be L11 times L51 plus L12, L52. But on the diagonal here, what we have is, well, let's go all the way out, L51 squared plus L52 squared, and then you've got all your other terms here. But the point I'm trying to make is the variance of an x. So let's just write this out. The variance of xj is simply going to be the sum of these loadings squared. This would be LJ1 squared plus LJ2 squared. So I can understand what the variance of the original x is simply by adding up the squared loadings. So that's the first result that you need to have. The next result, I'm not going to bother to prove. We use very similar formulas to the ones that I just stated over here, but since we haven't really covered those in this class, I'm not going to walk us through the proof. You can find those formulas in a multivariate analysis book or on the Wikipedia page. What's really important about this formula is that the loadings can be interpreted as the covariance between the common factor and that particular x. So usually we're standardizing our x's ahead of time, and so you'll recall that when we standardize our x's, the covariances are just correlations. And so usually we interpret these loadings as correlations. It's just telling me how is x sub j correlated with factor x sub I with factor f sub j. All right, let's go look at a specific example. And so this is a covariance matrix. It is not a correlation matrix. The reason we know it's not a correlation matrix is because the diagonal elements on this are not ones. So remember, correlation matrices have diagonal, have a diagonal of 1 on it, and everything off diagonal has to be between -1 and +1. So this is a covariance matrix. And so the whole idea here is we seek a set of loadings. So here is a loading matrix. Let's not worry about how I got this for now, such that I can almost reproduce this covariance matrix by knowing these lower dimensional loadings. So if you don't believe me, I've gone over to R and I typed in, let me just show you what I did here. I typed in that L matrix, so here's your loading matrix. And I was, we could have done this by hand. Maybe I suggest you do it by hand. I've also constructed this diagonal psi matrix. So here's that diagonal psi matrix. And let's just go compute this formula that we derived on the previous page. So if I take L times L transpose plus this diagonal matrix, so this is going to be a 4×2 times a 2×4, which gives us a 4×4 quantity. And this diagonal is obviously 4×4 as well. And notice we have just reproduced the original matrix. So the way to think about this is this two-dimensional thing is telling me most of what I need to know about this four-dimensional thing. So we're doing some dimensionality reduction, but we're kind of starting at things differently. We're starting with the common factors and reproducing the x's, as opposed to what we did with PCA, where we took our x's and then we did some sort of a transformation on that, the eigenvector rotation matrix and all that. Okay, so a couple more things. These sum of squared loadings are called the commonalities, and so this is the variance that is in common with other variables. So the variance in some x that is common to the other x's that I have. So if I'm very good at, say math problems, then this math factor would explain my performance on a bunch of x's, and those x's would be correlated. Likewise, if I weren't so good at math, then my scores would not be so good, and that's reflecting that correlation that's being explained by these factors that I have. The psi's are the unique variances. So let's just go back to this problem here. So if I take the sum of the squared loadings, so remember that's what I did over here, L11 squared plus L12 squared, so that would be 4 squared plus 1 squared, so that's 16 plus 1. That's the commonality. So that's the amount of variance in x1 that is common to these two factors. Now, the 2 over here in my psi matrix is what is unique about the variance of x1. Now, we can add these two up. So 16 plus 1 is 17, plus 2 gets me to the original variance of x1, which is 19. And then what we could do is come up with something like an r squared. So you might want to say, might want to ask, what fraction of the variance in this x1 variable is due to these two factors? And so the answer would be, I can explain 17 of the 19, or 89% of the variance in x1, knowing these two factor values. Okay, the other thing that I want to point out is that these loadings, so the loading is just the covariance between the x's and the f's. So what we could say is that the covariance between x1 and this common factor is 4. The covariance between x1 and the second common factor is only 1, and that's coming from this top row of my matrix. The example, there's another example on this page which shows some problems with the model. I don't intend to go over that in this video. All right, well, how do we estimate this common factor model? Well, I want to begin by pointing out there's a certain indeterminacy problem. So this indeterminacy problem is that I can stick an orthogonal matrix. So an orthogonal matrix means that, well, if T is this orthogonal matrix, T transpose times T is the identity. So I could easily stick a 1 in here. So this identity is like a 1, and then I could split it out. So this T transpose T is like sticking a 1 in it, but I could separate out the first part, so L times T, and then T transpose times L transpose. And the point I'm trying to make is this is also a decomposition of this covariance matrix that follows the same form, but these loadings are different. Okay, so we have a terrible indeterminacy problem in that once I determine this, these loadings, I can rotate them, an infinite number of ways, and it would appear like I have an infinite number of solutions to this problem. So what you want to think about is we're going to first determine the subspace, this k-dimensional subspace that describes the x's, and then we're going to pick a way to parameterize it in terms of what rotation we want to use. All right. So we'll fix the subspace and then rotate it however we like, and there's lots of ways that we can do this. As you noticed in my previous video, we talked about even using non-orthogonal bases to parameterize that subspace. Well, how do we actually find the subspace? So let me just mention that this is a holy war. There have been more articles written about the virtues of one approach versus another over the past half a century or so than I won't say any other topic in data mining, but this is certainly towards the top. So one approach is to use principal components analysis to find this lower dimensional subspace. And so actually most of the time when you run a factor analysis, a quote factor analysis in software like SPSS or SAS, you're really just running a principal components analysis, but they call it a factor analysis. So if you use the default configuration, you get a PCA. And so basically what we do is we find the PCA lower dimensional subspace, and then we pick a rotation that we like. Now, there is another approach which is called maximum likelihood. So you can watch my videos on maximum likelihood for other problems like logistic regression. There's another video out on my website that just talks about finding the maximum likelihood estimates of some distribution. And so what we do is we assume that these x's have multivariate normal distributions, we write out the likelihood, and we maximize it. And so that's another way of finding it. There are many other ways to estimate the solution to this. So the squared multiple correlation approach. So if you look up in the SAS reference manual for proc factor, you're going to see it offers probably about a dozen different ways that you can estimate this subspace. It's not an easy problem, and that's why so many solutions have been proposed. I want to mention one more thing about these methods of estimation. If you go to the Wikipedia page on factor analysis, there is a whole section that summarizes the the arguments for or against maximum likelihood, and refer to a classic paper in 1999 that discusses these. So I'd now like to illustrate this factor analysis model with a numerical example. I think one of the benefits of factor analysis is that it explicitly allows for different variables to have different amounts of measurement error, or different measurement accuracy or precision. So let me make that really clear. So our model states this: the x's are some function of this unobserved thing plus some errors, and these errors have different variances. So the variance is like the typical amount of noise. So if the variance is small, that means some x is very precise. Whereas if another x had very large variance, that would be not a very precise measure. So I'd like to cook up a data set where I have different x's with different levels of accuracy. It'd be like having different measuring devices where some were very accurate and others were very inaccurate of measurement error. So what we can see is that x1 is going to have a variance of 1/2 squared, whereas x5 is going to have a variance of 1/6 squared. Therefore, x5 is a much more reliable measure of f than x1. So you can see how I've cooked this data set. I want to generate a lot of data so I don't have a lot of sampling error in my estimates, and that way we can see if we can recover these true parameters and how exactly they get recovered. So what you'll see is I've generated 10,000 values of my factor. This would be like your math ability as an example, and I've generated them from a standard normal distribution, so mean zero, variance 1. Then what I've done is I've added, I've computed my x variables as the common factor f plus the specific error, and you'll see how I've just generated 10,000 random variables and divided by whatever I want to make the standard deviation and variance work out right. To estimate a factor analysis model with maximum likelihood in R, you're going to use one way of doing this is to use the factanal function. And so you'll see you specify a formula-like model, and then you tell how many factors you want. So we want one factor here. And let's go look at our results. So these loadings should give the correlation between the x's and the factor score. So to test this, I went over to R, and what I show are the factor loadings up here. Here's a correlation matrix between these true factors that I wouldn't ordinarily be able to observe and my x's. And so what you'll see is that these correlations, so 0.898, 0.948, all the way 0.986 something or other, are the factor loadings. So that's just saying how correlated is each one of these x's with the f. All right. Well, the other thing that we could easily compute are the commonalities. So the commonalities, remember, are the loadings squared. Now, if I had more than one factor, I'd have to square the loadings and add them up. But since we only have one factor, I just square the loadings to get the commonalities. So the interpretation of this is that about 80.6% of the variance in x1 is explained by knowing the common factor f. Whereas you're going to see x5, since the measurement error is so much smaller, we can explain 97.3% of x5 if we could know the common factor. All right, now I'd like to show how we can recover these variances that I mentioned. All right, so fit dollar uniqueness gives us the uniqueness values, and so notice the uniquenesses plus the commonalities equals 1. Why 1? Because I've standardized my data before doing a factor analysis. That's the default in just about every software package that I've used. And so the commonalities plus the uniquenesses equal 1. But that's not exactly what I'm observing here. Okay, so what we have to do to get back to what we had before is we're going to think about these commonalities as being like an R squared. It's not the raw variance. Okay, so I am going to take 1 plus the variances. And so 1 over 1 plus the variances would be computing the true fraction of variance explained by the data. And so you're going to notice these values match the commonalities very closely. I'll just show one more thing, which is the correlation between my estimated factor scores, which are stored in the scores part of the list, and the true factors, which in real life I wouldn't get to observe. All right. I've also run this with PCA, and what you'll see is that PCA really doesn't get the estimates of the uniquenesses or the commonalities right. I've also correlated the scores that I get from factor analysis and PCA, and the correlation of them is 0.9967. So even though the estimates of the uniquenesses and the commonalities are not right, the factor scores are practically identical, at least for this example. And I'm sure there are examples in the literature where the differences are greater. I'll just close with some commentary from very famous multivariate analysis book, Johnson and Wishern. And what they suggest is trying both. It's always prudent to see if one method produces a very different solution. If the solutions match up, that's great. Your findings are robust. Otherwise,